Last time I had derived using the method of images a problem where I put a charge above a ground plane that is grounded, and worked out that if you place an image charge with the same magnitude of charge but opposite sign, that the potential is 0 due to these two charges at z equals 0. And so I removed the ground plane and calculated electric field everywhere. The answer looks like this at z equals 0. So basically this is z. So at the observer point, so on the plate. So what it says is that the electric field is purely in the z direction. So you have attractive force towards this negative charge, repulsive force from this positive charge, and when you add them up, the electric field is in the negative z direction. So that is what you see, z hat with a minus sign. Now this is fine, but an interesting question to ask would be, if I place a charge q above a grounded plane, what kind of induced charges are created? I know that I am going to have negative charge, because Gauss's law tells me if I take a sufficiently large surface so that the potential goes to 0, the field goes to 0, I know that the field is going to go to 0 very fast, because I expect that charges will come in from the ground and I will get negative charges out here. So there won't be any net electric field going out, which means the charge enclosed is 0, which means I expect minus q on this plate if I have q placed above it. But I do not know exactly how that minus q charge is present. I do not know if all the minus q is in one point here, or perhaps the minus q is out here. So in order to find that out, I take the solution of this problem. I know the electric field on the plate, and on the plate, if I use Gauss's law, the bottom surface is inside the metal, there is no electric field. The top surface, there is an electric field, and on the surface there is charge. So I know already that Ez at plate is equal to sigma induced divided by epsilon 0. So sigma can be solved for, and sigma is nothing but epsilon 0 Ez. But I already know Ez. The entire electric field is in the z direction. So if I write it down, this is what I get, that the charge induced is q over 4 pi times a constant minus 2 z. Z is the distance, the charge is above the plate, so it is a constant, divided by r squared plus z squared to the power of 3 halves. So what is that going to say about our charge distribution? If I redraw the picture, I have the charge q, I have the plate, this is the distance z. On this plate, I am going to have negative charge, and the negative charge is going to look like this. This is minus 2 qz over 4 pi times r squared plus z squared to the power of 3 halves. So you can see that the induced charge on a plate is not a simple thing at all. It is a distributed charge. There is little charge out there, there is more charge out here, there is a lot of charge out here, less charge here, very little charge there. It distributes itself, it smears itself out, most of the charge being near where Q is. If I asked how much distance do I have to go in r before the induced charge drops to half its value, this is the maximum value, I will take half its value and draw a line. And then I ask how much is this distance. So, I would like to know this distance, which is the distance at which the induced charge becomes half. Well, if we look at this picture, at this expression, we know that sigma is proportional to 1 over r squared plus z squared to the power of 3/2. I can take the z below, so I can call the same expression as 1 plus r over z to the power of 3/2 times some constants. The constants will be q over 4 pi, then there will be a minus 2 and 1 over z squared. Now, if you look at this expression and say that this must be equal to 1 over 2, at r equals 0 it is 1. So, I want to know where it becomes half. Then what do I get? I get 1 plus r over z to the power of 3/2 must be equal to 2. That is, I take both denominators to the numerator. I have an expression that is to the power of 3/2. If I take this whole equation to the power of 2/3, then what do I get? I get 1 plus r over z to the power of 3/2 whole to the power of 2/3 is equal to 2 to the power of 2/3. As you know, when I take some quantity alpha to the power of a whole to the power of b, this is nothing but alpha to the power of a times b. So, 3/2 multiplied by 2/3 is 1, and so I get an answer which says 1 plus r over z is equal to 2 to the power of 2/3, or r over z is equal to 2 to the power of 2/3 minus 1. Now, it is not exactly 1, it is a little less than 1, but of the order of 1. So, you have to go a distance somewhat less, but of the same order as the distance the charge is above the plate before you will find that the induced charge has dropped to half its value. So, most of the charge is in a region that is of order in width the height of the charge above the plate. This is very common. So, you should know this as a kind of rule of thumb, that the induced charge on a conducting surface is concentrated in the vicinity of the actual charge. So, if I put a charge 1 centimeter above a plate, you will find that there is induced charge roughly within on a circle 1 centimeter radius on the plate. So, if I put a charge up there and I have a plate, this charge is nearest to this point on the plate, well, there will be a circle where most of the induced charge is present. And if you go further away, there is much less induced charge. Okay. So, that leaves actually 3 topics that we still need to cover in electrostatics. and I am going to cover one of them today, and that topic is Poisson's equation in 2D. When I say Poisson's equation, it is also Laplace's equation. Now, let me motivate the problem. Supposing I have a cylinder, and supposing I ground the side walls, I ground the bottom wall, and I apply a voltage V to the top wall. Now, this is actually one of the forms in which capacitors came initially. When initially people were trying to prove that charge could be stored, they created Leyden jars, and Leyden jars were nothing but bottles where they would put in an electrode. Here, instead of putting an electrode, we are just making the top our electrode. I would like to know the capacitance of this object, but how do I do it? If I write down the equation for that has to be solved, the equation is del squared phi is equal to 0. There is no charge inside. So, I had electric field was minus grad phi, and divergence of D was equal to 0, and D was equal to epsilon E. So, if I combine all three equations, I get Laplace's equation. Now, this is to be written in cylindrical coordinates, it is not in Cartesian coordinates. So, the equation looks like 1 over r partial derivative with respect to r del phi del r plus 1 over r squared del squared phi del theta squared plus del squared phi del z squared is equal to 0. So, this is a complicated equation, and along with this complicated equation I have the boundary conditions that phi goes to 0 when r goes to a, where a is the radius of the cylinder, phi goes to 0 when z goes to 0, and phi goes to V naught when z goes to L. So, I have an equation, a complicated equation, and rather complicated conditions on that equation, and I want to know how to solve such a problem. Now, there is a very standard way by which we have developed to solve such a problem. I will give you the concept first and then I will work out the details. The idea we have is that if you look at Laplace's equation, you can find, let us take the simplest case in Cartesian coordinates, d squared del squared phi del x squared plus del squared phi del y squared equals 0. If you look at this, you have two second derivatives which added together give you 0. So, you can immediately write down something. You can say del squared phi del x squared less than 0, del squared phi del y squared greater than 0, or del squared phi del x squared greater than 0, del squared phi del y squared less than 0. Why is this important? Well, it is important because we know that if you have spring like behavior, oscillatory behavior, sines and cosines, the second derivative of the function is negative, whereas if we have exponential behavior, the second derivative is positive. So, what it means is that Laplace's equation intrinsically contains two kinds of functions. It contains oscillating functions, periodic functions, and it contains non-periodic growing functions. What we are going to do is we are going to make a guess. Let us just look at some general solution to this problem. Well, I'll state that more precisely. I am going to guess that this potential phi has two different behaviors, one which is oscillatory in x, one which is growing in y. I am going to pretend that each is independent of the other. So, I will say that this phi is actually equal to some x of x, y of y. These are capital X, capital Y, this is small x, small y. So, these are two unknown functions, but the important thing about these functions is phi itself is a function of both x and y, but I am going to guess that it is a product of two functions. It is a product of a function that is only depending on x and a function that only depends on y. Why do I assume this? I assume this because of looking at this, I can see that there are two different behaviors that seem to be present. So, if I were to sketch this in x and y, supposing in x del squared phi del x squared is negative, it means phi is doing this. As I move in x, phi reaches a maximum and comes back down. But if I look at del squared phi del y squared, if this is negative, this must be positive, which means phi must actually be reaching its minimum and going up. So, at this point there are two very different behaviors in x and y. Such points are called saddle points, and Laplace's equation defines a function which is a saddle point at every point where it is defined. So, every point for phi is a saddle point. Now, if we put this assumption in, what do we get? I am going to substitute this into this equation. So, I get del squared del x squared of capital X capital Y plus del squared del y squared of capital X capital Y is equal to 0. Now, capital X is a function of small x, but capital Y does not depend on small x. So, when I take a derivative with respect to small x, y can be pulled out. Similarly, capital X is not a function of small y, so it can be pulled out. So, I can write this as y del squared capital X del x squared plus x del squared del y squared of capital Y is equal to 0. Now, I will do one more thing. This is still a function of y and of x, and so it is all mixed up. So, I am going to divide this equation by phi itself. So, I am going to multiply 1 over phi of x y times this. Since the bracket is equal to 0, if I divide it by phi, it is still 0, but phi is equal to x times y. So, if I divide by x times y, one y will cancel out and I will get 1 over x. So, I get 1 over capital X del squared capital X del x squared plus 1 over capital Y del squared capital Y del y squared is equal to 0. Now, there is something very remarkable about this equation. This part of the equation depends on x, depends on x, depends on x. It does not depend on y at all. This part of the equation depends on y, 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 does not depend on x at all. So, I have a form that looks like some function of x plus some function of y is equal to 0 for all x and y. Why do I say for all x and y? I say that because Laplace's equation must hold at every point. Therefore, the equation I had got, which is 1 over capital X d squared capital X dx squared plus 1 over capital Y d squared capital Y dy squared is equal to 0, must actually hold for every x and every y. It is not at some special x and special y. But this kind of equation cannot really be true. For example, supposing f were 3 at x equals 0, then g must be equal to minus 3. So, let us say f of 0 was equal to minus g of 0 is equal to 3. Now, what is the value of f at x equals 1? Well, supposing f of 1 was equal to 4. Well, it is not possible, because if f of 1 is 4, g of 0 is still 3 minus 3. So, 4 minus 3 is 1, but the point x equals 1 y equals 0, this equation must hold. So, I can't have 4 minus 3 equals to 0. So, this can't be true. It must be true that f of x is equal to f of 0 equals 3 for all x. Similarly, g of y equal to g of 0 equal to minus 3 for all y. What you can conclude from such equations is f of x and g of y are constants. They cannot depend on their variable, because if f of x depended on x, there is no way g of y can compensate. We need the sum to be equal to 0. So, if f of x varied, g does not depend on x, so it cannot vary, and it will fail when you apply the condition. Now, when writing this equation, I have gone over from del x del little x to full derivatives d dx. The reason is capital X is a function only of one variable and capital Y is a function only of one variable. So, when I take the derivative of a function of one variable, I do not need to put partial derivatives. There is nothing wrong in putting the partial derivative, it is just not necessary. So, this argument tells us 1 over x d squared x dx squared is a constant, 1 over y d squared y dx dy squared is also a constant. So, let us give that constant a name, that is, let us say that this is equal to minus 1 over y is equal to some k squared. Then I would get d squared capital X dx squared minus k squared capital X is equal to 0, d squared capital Y dy squared plus k squared y equals 0. We can see that important difference in sign, because when you add up these quantities, that is, when I multiply by y and I multiply by x, and add up these equations, this side gives me Laplace's equation, whereas these two cancel out. So, that is why I must have this difference in sign. So, one of them is minus, one of them is plus, but the term that has minus sign, it implies that x goes like e to the power of kx e to the power of minus kx, whereas the y equation implies y goes like sin kx cos kx. Once again, this is what we have been saying, namely the sin kx function looks like this, the e to the kx function looks like this. So, at every point one side is turning up and in another direction is turning down. So, every point is a saddle point. All right. So, this was a Cartesian geometry case, but I really want to solve this problem. I want to solve the problem of a cylinder whose sides and bottom are kept at ground potential, whose top is kept at a voltage V naught. How do I do it? I follow the same procedure. First, I say axial symmetry so phi not a function of theta. Since if I rotate the cylinder, it looks like the same problem, the answer cannot depend on the exact value of theta. So, phi may be a function of r and z, but it cannot be a function of theta. So, my Laplace's equation becomes 1 over r del del r del phi del r plus del squared phi del z squared is equal to 0. Once again, I will assume phi is equal to r of r, z of z. Substitute into the equation. So, I get 1 over r del del r del del r of capital R capital Z plus del square del z square of capital R capital Z is equal to 0. But z is a function of small z, and everything here is taking derivatives with respect to r. So, this z can be pulled out. R is a function of capital R is a function of small r only. Derivative is with respect to z. So, this capital R can be pulled out. So, I will do that and I get capital Z divided by r del del r of r del capital R del r plus capital R del square del z squared capital Z is equal to 0. Once again, we divide through by phi. The reason for dividing by phi is I still have terms which are dependent on both z and on r. I want to get the answer in the form of something that is a function of r plus something that is a function of z is equal to 0. Then I can separately equate them to constants. So, I will divide by phi. If I divide by phi, I am dividing by rz. So, the z cancels out and I get 1 over capital R, and here the r cancels out and I get 1 over capital Z. Once again, this is function of r and this is function of z. So, since each is a function only of one of the two coordinates, each is a constant. So, what does that give us? We get two equations. We get 1 over r d by dr, 1 over r capital R, r d capital R dr is equal to minus 1 over capital Z d squared capital Z d z squared, and I am saying that that is equal to k squared. So, I can make this into two separate equations. One equation says 1 over r d dr of r d capital R dr minus k squared r is equal to 0. Well, let me make this minus sign. So, this becomes plus k squared r equals 0, and the other equation is d squared capital Z d small z squared minus k squared capital Z is equal to 0. Again a plus and a minus. We always have to have that difference in sign, because if I multiply this by z and this by r and add them up, I should get back Laplace's equation. This second equation has an immediate solution. It says capital Z is equal to e to the kz or e to the minus kz. That is what this is. It is the equation for an exponential. And if you solve this problem, I am not going to tell you how to solve it, but you can solve it. You will find that capital R is equal to what are called Bessel functions, J0 of kr and y0 of kr. Bessel functions are like sines and cosines, except they occur naturally when you talk about cylindrical geometry. In Cartesian geometry, the natural oscillating function is sin kx and cos kx. In cylindrical geometry, the natural oscillatory function is j0 of kr, y0 of kr. And similarly, there are naturally oscillating functions in spherical coordinates. All right. So, we have got a solution. Now, what is our phi? Our potential phi is equal to some constant C1 e to the kz plus another constant C2 e to the minus kz multiplied by yet another constant j0 of kr plus a fourth constant y0 of kr. And in this expression, I do not know C1, I do not know C2, I do not know D1, I do not know D2, and worst of all, I do not know K. In fact, I know hardly anything. It is a very embarrassing situation. I have solved the problem, but it is of no use to me. If I am going to make some use of this solution, I have to put in extra information. But I do have extra information. I know that the potential goes to 0 at the bottom, I know that the potential goes to 0 at the sides, and I know that the potential goes to V0 at the top. So, first of all, I want to make this potential go to 0 at z equals 0. phi which is equal to r of r z of z equals 0 at z equals 0. Now, how can this happen? Phi can go to 0 at z equals 0 in two ways. Either z of 0 equals 0, that is one way in which potential can go to 0 at z equals 0, or r of r equals 0 for all r. If r is identically 0, then also phi will go to 0. They are the only two ways in which this potential can go to 0 at z equals 0 for all r. Now, obviously, if r of r goes to 0 everywhere, then I do not have a potential. That is a useless kind of function. I want something more interesting than that. So, I throw this out. I am not going to accept such a kind of solution that says there is no potential anywhere. So, I translate from a condition on phi to a condition on z. Z goes to 0 at z equals 0. This function is equal to 0 at z equals 0. Now, I am sure you have studied about exponential functions, and you know that you can construct trigonometric functions from exponential functions. You can construct e to the j k z plus e to the minus j k z over 2, that is cos k z, e to the j k z minus e to the minus j k divided by 2j, that is sin k z. Similarly, you can also construct e to the k z plus e to the minus k z over 2, and that is what is called the hyperbolic cosine, cosh, very important function, and e to the k z minus e to the minus k z over 2 is equal to the hyperbolic sine. So, these are all related to exponentials. These two are complex exponentials, they give you sines and cosines. These are real exponentials, they give you sine hyperbolic and cosh hyperbolic. Now, if you graph these, you know how cos and sine look like, but this is how cosh and sine look like. Cos hyperbolic, you can see that the exponential looks like this, and exponential of minus k z is a mirror reflection of this. So, this is e to the k z and this is e to the minus k z. So, if I add these two functions together, I must get a function that looks like this, and that is what the hyperbolic cosine looks like. At z equals 0, both of these are 1, so 1 plus 1 divided by 2. So, the cos hyperbolic is equal to 1 at z equals 0. The cos hyperbolic grows like an exponential both ways. For large values of z, it is like e to the k z over 2, because one or the other becomes nearly 0. What does the sine hyperbolic look like? Well, we can plot it again. E to the k z looks like this, minus e to the minus k z is reflected and changed in sign. So, it looks like this. Now, if I add these two together, I have not drawn it properly, the 0 should, this point there is equal amounts above and below. So, they add up to 0. For very large values of z, it is basically this function or this function. So, if I plot the function, it is going to look like this. It is like e to the power of minus k z over 2 for large negative values of z. It is like e to the k z over 2 for large positive values of z, and it is 0 at z equals 0. Now, it is this thing that is important. When I write it as hyperbolic sines and cosines, this function goes to 0 at only one point, and that one point is z equals 0. And I want a function of z which is a combination of exponentials which goes to 0 at z equals 0. So, I can replace this entire function by some constant c sine hyperbolic kz. Now, there are similar arguments that you can apply which will allow you to eliminate this function. So, it turns out that the final form of your expression will look like sine hyperbolic kz times the Bessel function of kz. I am not going to go into Bessel functions because that is an advanced topic. It is not really suitable for this course, but you do not really need to know what a Bessel function is. This is a wiggly function. It is a function like a sine or a cos. All right. Now, what do we do with this? We still have not solved the problem. Why not? Because we had 3 boundary conditions. We had a boundary condition that phi was equal to 0 at z equals 0. That is taken care of, sine hyperbolic of kz. We had a condition that phi equals 0 at r equals a, and we had a condition phi equals v naught at z equals capital L. Now, we actually had a fourth condition which was that phi behaves itself at r equals 0. That is why I was able to throw out the other Bessel function. If you look at Bessel functions, this Bessel function is just a sinusoidal like function, but the other one blows up at 0 and then interleaves with j0. So, this function you cannot accept because at r equals 0 it goes to infinity. So, that still leaves us with two other boundary conditions. Phi must go to 0 at r equals a, and phi must go to v naught at z equals L. And that does not seem to be enough. I now have only 2 free variables, c and k. What can we do? Well, if you look at what j naught is, j naught is an oscillatory function. This is j naught of any argument u versus u. So, if kz were equal to these values, if j naught of kr, if kr were equal to zeros of j0 of kz, then r of r equals 0 at r equals a, and phi goes to 0 at r equals a. So, this should be r at r equals a. So, I just put it as K A. So, let me repeat. I have a general form here. This general form satisfies the boundary condition at the bottom, but it does not satisfy anything else. But I am free to choose my K. So far I have not selected it. If I look at the plot of any oscillatory function, oscillatory functions go to 0 now and then. Sine goes to 0 at n pi, cos goes to 0 at pi over 2, 3 pi over 2, etc. Similarly, j0 goes to 0 at certain values. If I set Ka equal to these values, okay, if Ka is equal to the zeros of J0 of u, then J0 of Ka will be 0, which means this piece goes to 0, and therefore potential goes to 0. Now, there is only one problem with this idea. It is a wonderful idea. I have taken care of one more boundary condition, but there are many zeros. There is not one zero, there are infinite number of zeros. So, instead of reducing my problem to solving one constant, I suddenly find myself with an infinite number of constants to solve for. If I call each of these zeros, if I call Ka equal to lambda 0 n, meaning the nth zero of J0, then my phi has now become something more peculiar. It becomes C sub n sine hyperbolic of Kz J0 of lambda 0 n r over a, and this k is the same k after all, must therefore also be lambda 0 n over a. Phi does not know anything about n, but suddenly I have introduced a new variable called n, and I know no way of handling this unless I sum over all n's. Now, the left hand side does not know about n, right hand side does not know about n either. It is a dummy index. This now gives me all possible solutions of Laplace's equation which satisfy phi equals 0 at the bottom, which satisfy phi equals 0 at the walls, which has phi behaving itself at the origin, and phi is equal to something, we do not know what, at the top. But actually we also require phi equals V naught for all r at z equals L, and that is the final part of the puzzle. We need to pin down what values of Cn to use such that phi is equal to V naught for every value of r. I am not going to solve this problem. In fact, the reason for presenting the cylindrical problem before I went back to Cartesian is that the Cartesian problem is too easy, and because it is so easy, you do not understand what is happening, what is the underlying idea in it. Now, I will repeat this whole process for the Cartesian problem, and I want you to watch carefully how we are doing the same steps, we are making the same arguments, except that since they are sines and cosines, we know all about them. So, I am now going to take up a problem where I have conducting walls. This is the origin, this is x, this is y, this is x equals Lx, y equals 0, this is x equals 0, y equals Ly, this is Lx, Ly. Within this region, I have del squared phi equals 0, and I have 3 walls are grounded, and the 4th wall is held at some voltage V naught. It is exactly the same problem as the cylindrical problem, only changes instead of Rz I am talking about x and y. The equations are much simpler. I now have del squared phi del x squared plus del squared phi del y squared is equal to 0. If you go back to your notes, you will see earlier in the lecture I worked out what you have to do, and we found out that we assume phi is equal to some capital X of x, capital Y of y, and when we work through all the details, we find that d squared capital X dx squared is equal to minus d squared capital Y dy squared is equal to minus k squared. I could have put plus k squared, but I know beforehand I want minus k squared, so I have put it there. So I get two equations. The two equations are d squared, sorry, this is 1 over capital X and this is 1 over capital Y. D squared capital X dx squared plus k squared capital X is equal to 0, and d squared capital Y dy squared minus k squared y equals 0. We had reached up to this point even earlier. The solution of this equation is the pendulum equation. So, we know the answers. Answers are capital X of x is equal to a cos kx plus b sin kx. This is the unstable pendulum equation. So, I again know the solution. It is y of y equals a e to the power of kx plus b e to the power of minus ky. So, I can now write down the answer for phi. The potential, which is a function of x and y, is now equal to a cos kx plus b sin kx multiplied by, this should be some c, this should be d, c e to the power of kx plus d e to the minus ky. Compare this with what we have already done. For the RZ case, we had a j0 of kx plus b y0 of kr times c e to the kz plus d e to the minus kz. So, exactly the same structure, but now I have to fit my boundary conditions. The same argument that allowed me to say capital Z of z equals 0 led to sine hyperbolic of kz will now allow me to simplify the y dependence, because I have a boundary condition where phi equals 0 at y equals 0. So, I am able to substitute this piece and replace it with some c sine hyperbolic of ky. But I still do not know what to do about the first part. Now, what are my conditions in x? I have phi of x equals 0 any y is equal to 0, phi of x equals Lx any y equals 0. Now, if I rewrite this, it is saying capital X of 0, capital Y of y equals 0, capital X of Lx, capital Y of y equals 0. As before, I can choose to make capital Y identically 0, but that is absurd. I will not have any solution after that. So, the answer must be this capital X of 0 equals capital X of Lx is equal to 0. Now, if you look at this form, and substitute 0 and Lx, what do we get? We get a plus 0, sine of 0 is 0, is equal to 0, and you have a cos k times Lx plus b sine k times Lx is equal to 0. The first equation tells us a is 0. There is no cosine. Since a is 0, this piece goes away. The second term says that b times sine of something is equal to 0. Now, I can set b to 0, but that is very bad, because then that says x is identically 0. So, we want sine k Lx to be 0. How do we make sine k Lx 0? I know that if I plot sine goes to 0 at periodic values. So, if I make k times Lx equals lambda 0 n, I am calling it lambda 0 n just to make it familiar, then I have solved my problem. In this particular case, I know what these lambda 0 n are, they are just nothing but n phi. I will complete the problem next time, but you can see where it is going, and we will get a full solution of this problem.